ancient Earth, you might say.
Wait a second, how did the solar system even get there?
One of the first philosophies concerning the formation of our solar system was introduced in 1755 by Immanuel Kant. Kant believed our solar system originated as a rotating cloud of gas and dust. These gases were mainly hydrogen and helium, and the dust was a mixture of chemicals similar to those which make up the Earth. This is known as the nebular hypothesis. As the cloud of gas and dust rotated, gravity accelerated the particles within it, causing the cloud to flatten into a condensed disk. The denser dust accumulated at the center of this disk, forming the protostar which we call the Sun. Under its own weight, the protostar compressed, becoming increasingly hotter and denser until its temperature reached millions of degrees. At this point, the center of the nebular disk, the protostar, was the densest and hottest. The outer part of the nebula was less dense and eventually began to cool down. Due to the cooling of the gases, they condensed into their liquid or solid state. Gravity caused the remaining dust to compress into kilometer-sized chunks, known as planetesimals. The inner planets of our solar system, closest to the Sun, were built up through collisions of these large compressed chunks. The giant outer planets, such as Jupiter or Venus, formed mostly from gases. Because each planet's orbit differs in distance from the Sun, their composition and formation are each unique. As it is the planet that we habituate, we will be looking more closely at the formation of the Earth and its moon, as well as the differentiation of elements of which they are composed.
About 4.5 billion years ago, the Earth was struck by a planetesimal meteor, approximately the size of Mars. The impact of the collision propelled a shower of debris from both the meteor and much of the Earth's mantle into space. The kinetic energy produced by the collision was converted into heat that caused melting to occur. As a result, the Earth was reformed as a terrestrial body with an outer molten layer hundreds of kilometers thick. The shower of the debris, as a result of the collision, remained within the Earth's orbit, held there by the gravity of the Earth's mass. The planetesimal collision increased the rate of the Earth's rotation and tilted the planet's axis of rotation by 23 degrees. Scientists call this theory the giant impact hypothesis. The debris that had drifted off into the Earth's gravitational force eventually aggregated to form the Moon. A smaller percentage of the debris collided and merged with the Earth.
Our knowledge of the exact composition of the Moon is still vague, but rock samples and data have been brought back to Earth by astronauts for research. Scientists discovered that the Moon has many of the same elements that Earth does. This suggests that the impact hypothesis is accurate. Due to the mountain ranges and basins on the Moon, we believe that there was once tectonic activity as Earth experiences today. Originally, the Moon was a body of magma, and as it cooled, the composition crystallized, causing the denser elements, such as iron and magnesium, to sink and compress as the core. The lighter elements floated to the exterior of the Moon and formed the crust. We believe the Moon is completely solid now because the landscape is unaltered unless there is a meteor impact or wind erosion.
Geologists have used seismic waves to determine the density of the Earth's layers. The crust is composed of oxygen, silicon, aluminum, iron, magnesium, and calcium, elements that were less dense than iron and nickel. As these elements rose to the surface, they cooled to form the crust, which ranges in thickness from about 7 kilometers on the seafloor to 40 kilometers on the continents. Oceanic crust is continuously generated by seafloor spreading, whereas continental crust is an accumulation of silicates with a felsic composition. The difference between the density of the two crusts is what helps drive the theory of plate tectonics. The mantle, which lies between the crust and the core, is composed of silicon, aluminum, iron, magnesium, calcium, and oxygen. It was formed as the more dense material sank to form the core, and the less dense material floated to the surface to form the crust. The mantle is about 2,850 kilometers thick and is composed of ultramafic silicate rocks, which contain more iron and magnesium than crust silicate rocks do. The outer core is composed mainly of iron, as well as nickel, sulfur, and oxygen. It is a liquid sphere. The inner core is composed mainly of iron with some nickel. It is a solid metallic sphere with a radius of 1,220 kilometers, suspended within the liquid outer core.
The unique formation of our planet Earth created the landscapes we see today, from the rugged mountains to the rolling desert dunes, vast oceans, and forested hillsides. Due to tectonic activity, the atmosphere that envelops the Earth, the protostar known as our Sun, and a variety of other fragile conditions, it is currently the only planet in our solar system habitable to humans. Now that we've led you through the formation of the Earth and its moon, we hope we've inspired you to expand your knowledge of the dynamics of the solid Earth.